Hello, in this video we're going to look at some probabilities for common casino games. I should start by saying that I don't endorse gambling, but it does give us a great opportunity to look at some probability mathematics in the real world. So the first one I have up here is roulette. Roulette is a game that we'll find in just about every casino. It's a wheel with 36 numbers colored black and white plus a 0 in European roulette and a 0 and double 0 in American roulette. So on the European wheel, they'll spin the wheel, drop a ball, and the ball will eventually land at one of these spots. There's 37 total possible outcomes, so that means our probability space, or the number of possible events, is 37. That's why the denominator in all of these fractions here is 37. In American roulette, the total number of possible outcomes is 38 because we have 36 colored numbers and then the 0 and double 0. So the denominator, or all the probability space in American roulette, is 38. And so if we're betting on a single number, then we have a 1 in 37 chance or 1 in 38 chance. And those chances, or the probabilities, roughly relate to the payouts. If we could bet on a 2, 3, 4, 5, 6 number combination, in which case the numerator just mimics the number combination that we're betting on, and the denominator stays the same because the total number of possible outcomes doesn't change on the roulette wheel. And so the probability increases as the number of winning events increases. If we bet on 6 different combinations, then we have 6 possible chances of winning. If we bet on a column, which we see here, we have a 2-to-1 chance, or 2-to-1 odds, 2-to-1 payout. Because we're betting on 12 possible numbers, that's roughly a 1 in 3 chance of winning, about 32%, 31.5%. Similarly, if we bet on a dozen, 1 through 12, 13 through 24, 25 through 36, in these spaces here, we have about a 1 in 3 chance of winning, which is, again, roughly 31.5% there because we have 1 additional and 2 additional spaces. We could also bet on half the numbers, 1 through 18 or 19 through 36. We can bet on evens or odds, reds or blacks, and those will give us roughly about a 50-50 chance. And so that's reflected in the payout of 1-to-1. Roulette is a fairly simple game as far as probability mathematics goes. If you want another tutorial, there's a very nice illustrated tutorial here. You can check that out. Craps is another very common casino game. Craps is slightly more complicated as far as probabilities go. We've got 2 dice. On each die you have 6 possible outcomes, 1 through 6. And then so here's our first die. Here we have a 1 in 6 chance of getting any of those numbers. And then for each of those numbers we can branch out on our tree diagram. So we have a combination of a 1 on the first die, and the second die could be 1, 2, 3, 4, 5, or 6. And so there are 6 different sums here. And so our probability space, or the total number of possible outcomes or events, is 36. And we can see our distribution here, with 7 being the most common, or the most likely roll for 2 dice. We've got 6 different ways to make a 7. 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, and 6, 1. 2 dice, sum equaling 7. The least common rolls are the 2, which is called snake eyes, or the 12, which is called boxcars. And so the way craps works is that you could win on your first roll if you roll a 7 or 11. So you've got 6 plus 2 possible ways to make 7 or 11, 6 ways to make 7, 2 ways to make 11, 36 possible outcomes. We're just going to add those probabilities together for 8 over 36, or 2 over 9, roughly 22%. You could also lose on your first roll if you roll a 2, a 3, or a 12. And so we've got 1, 2, 3, 4 possible ways to make a loss on the first roll. 4 out of 36 is roughly 1/9, or roughly 11%. And so if you don't get a 2, 3, 7, 11, or 12 on your first roll, you have what's called a point. 4, 5, 6, 8, 9, 10. And then you have to roll a point before you roll another 7. Remember, 7 is the most commonly occurring combination between the 2 dice. So you are most likely to roll a 7 on any given roll. And so if you don't win on your first roll, then you might have less luck on as far as winning goes. If you don't roll a 7 or 11 on your first roll, then your probability of winning on a subsequent roll is given by this equation here, and that was taken from mathworld.wolfram.com. So say you roll a 4 on your first roll. It's not a winner, you got a point, and you're looking to roll a 4 on your second roll. And so we take this equation from Wolfram. 3/36 divided by 1/6 plus 3/36 is 3/36 divided by, let's see, 6 times 6, 1 times 6 divided by 9/36. We're going to multiply by the reciprocal. We get, you can see here, we get 30.33. And then we're going to multiply that by the probability of rolling a 4 on the second roll. So we get a probability of win on that second roll of about 2.7%. Those probabilities increase as the chances of rolling a 5 or 6 or an 8 increase. Right? And so we can see that the sum of those winning on our second roll with a point is about 27%. So if we don't win on the first roll, then we have about a 27% chance of winning on the second roll. And then add to that the probability of winning on the first roll, and we get about a 49.2%. So it's almost 50-50 chance of winning on 2 rolls. Right? And so these probabilities won't show up immediately. These are over long terms, over large numbers. That's how our probability is distributed. But if you rolled dice 36 times, you would not come up with this perfect table. And so over the long term, then the casino has a slightly higher chance of winning, just like with roulette. That's why they added these numbers, the 0, the double 0, because the casino has to make a profit in order to stay in operation. And so the house always wins, not exactly, but the house always wins more than the players do in the long term. Here's blackjack. These are slightly more complicated probabilities. You can find these tables, these decision tables all over the internet that'll tell you when to hit, when to double down, when to stay, when to split. This one doesn't have splits, but that's for a separate lesson. So let's say we've got 6 decks in the shoe, right? And the more decks the casino uses, the more likely they are to win, which is why casinos are not going to use only one deck. Their odds of winning are much lower than if they have multiple decks. So let's say we have 52 cards in a deck. We've got 6 decks. That's a total of 312 cards in the shoe. And our card values, if the ace comes up, that's an 11 or a 1, depending on the player or dealer choice. 2 through 10 are face value, and then Jack, King, Queen are also face value. And so let's look at a first game here. So the dealer deals. The player has 2 up cards. The dealer has 1 up card, 1 down card. We don't know what that down card is. So say the player comes up with 17 right off the deal. And does the player want to hit or stay? Well, we can consult our decision table here. We've got the dealer showing 10, and so it says we should stay. Let's just try to figure out why. So we want to know the probability that the dealer will have greater than 17. And if we think the dealer has greater than 17, that would mean we want to hit, even though if we get greater than 4, we'll bust over 21 on blackjack. And so the probability of the dealer having greater than 17 is the probability of this X, the down card, being greater than 7. Number of cards in the deck that are greater than 7, well, we've got 6 aces, 6 kings, 6 queens, 6 jacks, 6 tens, 6 nines, 6 eights. So that's 1, 2, 3, 4, 5, 6, 7 cards. And then we have 1 showing here, 2, 3 showing. 6 times 4 times 7, we've got 6 of each of these for each of the 6 decks, plus 4 suits, clubs, spades, hearts, and diamonds, and then 7 values here. That's 168 possibles. Well, but we've got 2 knowns, we've got 2 knowns here that are greater than 7. So we're going to subtract those and get 166 still in the shoe, cards that are greater than 7. And so if we have 6 decks in the shoe, then we subtracted 1, 2, 3, and we're going to say we still don't know this one. It's as if it's still in the shoe because we haven't seen it. So there are 312 minus 3 possibilities, or 309 possibilities, still left in our space. So the probability of X being greater than 7 is just the simple possibility of all the cards greater than 7 from that total number of possibilities, or 166 over 309, which is roughly 54%. All right, so let's say if x is greater than 4, let's say we want to hit. This is a fairly good chance that the dealer could have greater than 17. So let's just assess the likelihood that if we hit, we'll bust or not bust. And so if x is greater than 4, then all of the cards left in the shoe are 4 or less. And so we have 4 possible hits: ace, 2, 3, 4. Remember, ace is a 1. We would automatically take a 1. And we got 4 cards, 6 decks, and 4 suits, so 4 times 4 times 6, or 96 non-bust events, given that x is greater than 4. And so the probability of not busting, given hitting on a 17, is 96. 96. If we know that x is greater than 4, then we've got 312 minus 4 known cards, or 308 possible events there. And so 96 over 308 is roughly 31%. So there's 31% of busting, or of not, excuse me, there's about a 31% of not busting if we hit on a 17. That's a pretty low chance. So there's, again, a greater than 2 out of 3 chance that if we hit on a 17, we'll bust. So if x is less than or equal to 4, it's roughly the same thing, except the number of cards in the shoe that are 4 or less is just 96 minus 1. And so we have 95 over 308, or about 31% again. Still roughly 69% chance of busting, hitting on a 17. And so since the chance of busting, if we hit on a 17, is greater than the chance of the dealer having 17, then we should stay. And that's exactly what the chart says here. Let's look at a second game. So the player had 15, dealer shows a jack, player had 15, then we hit, and we got an ace. And so we'll take that as a 1. We've got a 16 now. And we want to know, should we hit or stay? Well, we can consult the table again. Well, on a hard 16, we'll just call it a 16 to save ourselves the explanation of hard and soft here. On a 16, we should hit. It says if the dealer's showing 10. Well, let's just assess out the probabilities. And this is a pretty tough hand. This is a real narrow margin here. So the probability of D being greater than the dealer having greater than 16 with these 2 cards, well, is the probability of x being greater than 6. So if we stay, and if the dealer has less than 16, then he's going to keep on hitting until 17. But if it's less than 16, then the probabilities change. So let's just assess, first of all, if the dealer is beating us as is right now. So what's the probability the dealer has greater than 16? Well, we've got 6 decks, 8 cards that are 6 or greater. We've got 7, 8, 9, 10, jack, king, queen, and then ace. Right? If he has an ace, then that's a 21, and we lose anyway. But the ace in this case would be at 11, so it's greater than 6. We've got 6 decks, 8 cards with value greater than 6, and then 4 suits minus the 2 showing. 1, 2. This ace is actually a 1, and so we're not going to count that one. Divided by 307, right? So if we're assessing the dealer's probabilities, and the dealer already knows what he has or she has. And so then that equals roughly a 61, 62% chance of the dealer having greater than 16 as is. So what's the probability of hitting on a 16? And if we hit on a 16, then their 4th card is less than or equal to 5. Right? If we get less than or equal to 5, then we have a chance at getting a 21, or we won't bust. So if we hit, what's the chance that we don't bust? Well, we've got 6 decks again, we've got 4 suits, and then we've got 5 cards in the deck that are less than or equal to 5. We've got ace, 2, 3, 4, and 5. Right? And then divide by 307 for the 312 minus the 5 cards here. And we get about a 38% chance. I said minus 2 or 3 because we still don't really know what this is here. Right? Okay, so if this is an ace, then that would be 1, 2, 3 cards less than or equal to 5. If it is greater than 5, then it would be 1, 2 cards greater than 5. And so since we don't really know what the dealer has yet, we have 2 possible probabilities here depending on what that is. So the probability of not busting on a hit is about 38%. Probability of hitting and getting greater than 5 is roughly the same as what we had up here. Right? So we had 6 decks, 8 cards greater than 5. In this case, the ace is a 1, and so we're not going to say that it's greater than 5. Minus 2 or 3 because we have 1, 2, and a possible 3 here that are greater than 5. Divide by 307, we got roughly 62, 61.5% chance of busting giving a hit. So this is a really tough decision. We're going to say that player should hit because the probability of busting is either less than or equal to the probability of dealer having greater than 16. Remember, the dealer was going to hit until 17 anyway. So if the dealer gets 16, then it's not going to be a push to the next hand. The dealer is going to keep hitting. And so even with 50-50 odds here, then we should continue hitting. So the probability of not busting giving a hit on a 16 is equal to the probability of the dealer busting on a 15 or less. Let's take a look at if the dealer had a 15. So the dealer is automatically going to hit until 17. If the dealer had a 15, that means x is equal to 5, then the dealer is going to have to hit. What's the probability that that dealer is going to hit on a 15 and bust? Well, that's the probability that the hit is greater than 6. 6 decks, 7 cards greater than 6, 4 suits, minus 2, 1, 2 cards already showing, already out of the shoe that are greater than 6. Divide by 307 possible is 54% chance that the dealer busts on a hit of 15. And the probability that the dealer is going to win, that means that the dealer is going to have X as a 5, so that gives him or her 15. And then here she's going to pull a 2, 3, 4, 5, or 6 for the win over our 16 here. And so that gives us 6 decks, 5 cards in this range here, and then 4 suits, minus 2, minus this one, and if this one is a 5, that gives us 2. Roughly 38% chance. And then we could trace these probabilities down to 12, but it will only do one more here. If x equals 4, the probability of dealer busting on a 14 hit is the probability that the hit is greater than 7. 6 decks, 6 cards greater than 7, times 4 suits, minus 2 already showing, that's these two. Greater than, oh, sorry, that's these two. Greater than 7, divided by 307, which is 312 minus 5. Roughly 46% chance. You can see that the probability of busting as the total goes down also goes down. In this instance, the probability of the dealer winning on a 14, if he hits or she hits, is the probability, again, of getting a 3, 4, 5, 6, or 7. That's the same probability of winning on a 15 because it's the same number of cards in the ideal range there. The range just bumps up one. And so you'll notice this is the same probability as we had up here, the probability of hitting and getting less than or equal to 5. And so as the probability of busting decreases as x decreases, but the probability of the dealer's win does not exceed this here, as he or she has to get 17 or greater. And so this is the narrowest margin here, where even if we're at 50-50 odds, because the dealer has to hit until 17, then we're going to take the hit on a 10 showing, just like the chart shows it. Looking at 5-card poker. Well, some people say this is a game of skill. You still can't substitute luck. There's no substitute for the cards, having the cards here. As we can see from this chart that I made up, having absolutely no hand at all, just whatever your highest card is, you have roughly 50-50 chance of getting nothing in any 5-card deal, right? So if we're looking for single pair, that's the lowest, that's the weakest hand you could have. That's better than nothing at all. Single pair is just 2 cards of the same number, 3 cards of different numbers, and we're looking at combinations here, right? So we're going to say we've got 13 cards in a suit, right? We're going to choose one of those, and then we have 4 suits. And since we're looking for a pair, we're going to have, so we got choose one of the 13 cards out of the ace through king, and then we need 2 of those. So we've got 4 suits, and we're going to choose 2. And then the rest of the 3 choices here, well, we've got 12 left between the range of ace and king, and we're going to choose 3 others, and then we have 1 from one suit, 1 from another suit, 1 from another suit. Right, so here's our way of figuring out the number of hands, the number of possible pairs, right? So we've got over 1 million possible pairs, and the number of hands, the number of total hands, or the number of possible single pairs divided by the total number of hands, which would be 52 choose 5, 52 cards in a deck, we're going to choose 5. This is the total number of possible combinations dealing out 5 cards. And so if we take this number here, just over 1 million different single pairs, right? We could have 2 2s in several different ways. We could have 2 of hearts and a 2 of clubs. We could have 2 of hearts and a 2 of diamonds. We could have 2 of hearts and a 2 of spades. We could have a 2 of spades and a 2 of diamonds, etc. So there are many different combinations among each pair for a total of over 1 million different unique single pairs. And so we have 1 million divided by the 2.5, 2.6 million total hands gives us a probability of getting a single pair, which is roughly 42%, or the odds are roughly 1 in 2.37 of being dealt this hand. If we have 2 pairs, that means we have 2 cards of the same number and 2 other cards of the same number, and then 1 card difference. So we're going to say 13 choose 2. Remember, we have 13 unique numbers in a suit. We're going to choose 2 of those, then we're going to have some 2 suits to make our pair, and then our second pair, some other 2 suits, and then we're left with 11 out of 13 after we've chosen 2 of those cards, and we're just going to take 1 of those in 1 suit. Gives us a total of 123,000 different combinations of 2 pairs. We're going to take this number divided by the total number of hands, and we get about 4%, 4.7%, 4.8% chance of getting dealt 2 pairs. This is not with withdrawing or exchanging cards. This is just being dealt directly. So we've got about a 1 in 21 chance of being dealt 2 pairs. 3 of a kind, getting less likely as we go down the list here. 3 cards of the same number, 2 cards of different numbers. Again, we're going to start with 13 different cards. We're going to choose 1 of those, and then we're going to have that same card in 3 different suits. So out of the 4 suits, we're going to have that card in 3 suits. Then our remaining 2 cards, we're going to choose out of 12 total numbers, possible numbers, and then each of those is going to be unique, right? So we have 54,000, 55,000 possible ways to get 3 of a kind for a probability of about 2.1%, or 1 in 47.3 hands or deals. A full house is 3 cards of the same number, 2 cards of some other number. So we're going to start out with our 13 numbers. We're going to choose 1 of those, and then we're going to have that same number, whether it's a king or a jack or a 9 or a 2 or whatever. We're going to have that same number in 3 different suits. Our other 2 numbers we're going to choose from 12. So if we've got 3 threes, then we're going to need some other two numbers. We have 3 threes and 2 fours, and we're going to take that 4 from the 12 remaining possibilities. We're going to have that in 2 suits out of possible 4. Gives us about 3,700 possible combinations of a full house, or less than 1% chance of getting a full house, 0.1%, 0.14%, or 1 in 694 possible deals. 4 of a kind, getting less and less likely. That's 4 cards of the same number, 1 of a different number. Again, we're choosing 1 of the 13 different values, and we need that in all 4 suits. And then we've got 48 remaining, 52 minus the 4 cards that are of the same value in all 4 different suits. Gives us one possible pull from 48. So we're just going to say 48, choose 1 for the remaining card. That gives us 624 possible combinations for 4 of a kind, or a 0.024% chance, or 1 in 4,165. So if you played 4,165 games of poker, you probably won't get a 4 of a kind, or maybe you'll get it on your 5th hand, but then you won't get it for, if you played millions and millions of games of poker, then it would average out to every 4,165 hands you'll get dealt a natural 4 of a kind. A straight is 5 consecutive cards not of the same suit. For example, ace, 2, 3, 4, 5 in mixed suits, or 8, 9, 10, jack, queen in mixed suits. And so we're excluding straight flush and royal flush, and ace can be high or low in this case. So we've got 10. There are 10 different possible strings of 5 cards. among our 13 cards. We've got ace 2, 3, 4, 5, 2, 3, 4, 5, 6, 3, 4, 5, 6, 7, so on and so forth. There are 10 possible consecutive number combinations there. And then they're going to be in 5 different suits. So you've just got 4 times 4 choose 1, 4 choose 1, 4 choose 1, 4 choose 1. They're going to be in different suits, or not all the same suit anyway. This ends up being 10 times 4 to the 5th, and that gives us 10,240, but we're going to subtract the straight flush and royal flush, which we're going to look at in a moment. Gives us a possible 10,200 possible straights in a deck, or a slightly higher chance of getting dealt a straight than a 4 of a kind. 0.3%, actually quite a lot higher than a full house, dude. 0.3% chance of being dealt, 0.4% chance of being dealt a straight, or 1 in 254.8. A flush, but not a straight. A flush is 5 cards of the same suit, they're non-consecutive, so we have 1 suit, so we're going to say 4 choose 1. Right, 1 out of the 4 suits, and then we've got, within that suit, we've got all 5 cards. And then we're going to subtract from that the 10 straights. Remember, there are 10 possible consecutive combinations within each suit. And so we get 5,108 possible flushes, or 0.19% chance, or 1 in 508 hands. You get dealt a natural flush. A straight flush is 5 cards of the same suit in consecutive order, but not the highest 5. The highest 5, ace, king, queen, jack, 10, is called a royal flush. And so if you've got 5 cards in the same suit and they're in consecutive order, well, then we've only got 9, because that's 10 minus 1 straights. 10 minus 1 straights is 9 times 4 suits, so we've got 36 possible straight flushes, and then the royal flush, and that's a very low chance, 1 in 72,000 hands you get dealt a natural straight flush. Finally, a royal flush is the same as a straight flush, but it's the top 5 highest cards, ace, king, queen, jack, 10, in the same suit. So we've got only 4 possible scenarios here, right? We've got, you need all 5 of these cards, and you've got 4 suits, so there are only 4 possible ways to get dealt a royal flush. That's the least likely hand to get dealt in a game of poker, 5-card poker. And that, around 650,000 hands, you'll get dealt a natural royal flush. It almost never happens. Usually, most often, more than 50% of the time, you will not have anything. And so just whoever bluffs the best, or which is where the skill comes in, whoever bluffs the best, or whoever's luckiest to have the highest card then. And there are many different rules and types of poker. And again, I go back to my initial proclamation that I don't endorse or condone gambling, but it does give us a great chance to use probabilities in the real world. And so now maybe you learned a little bit about why casinos are profitable, because the odds are always in favor of the house. The house designs the games, the rules of the games, and the rules of betting in order to make the chance of player winning lower. And so these couple games here, about 50-50 chance. Blackjack, I've read the house has about 0.16% higher chance of winning over the long term, and then they've got all these different double down and split rules in order to increase their chances of winning if you don't know the tables very well. And then with poker, well, that depends who you're playing against, what kind of rules you're playing. But in the long run, gambling is never a winner except for the casino. Okay, thank you.